So with that, I'm going to introduce Dr. Erica W. Carlson, a professor of physics and astronomy at Purdue University. She obtained a BS in physics from Caltech, and then a master's in physics and a PhD in physics from UCLA. She did postdoctoral research at Boston University, Department of Physics, before she moved on to a professorship at Purdue University in 2003. So going on 20 years at Purdue. Her research focuses on superconductors, liquid crystals, and strongly correlated materials. I'm not sure what all of that means, but we may hear some of it perhaps today, I'm not sure. She's also known for her work in physics education, especially quantum physics, and her use of innovative technologies in physics education. She is a fellow of the American Physical Society, a nonprofit membership organization working to advance and diffuse the knowledge of physics through its outstanding research journals, scientific meetings, and education, outreach, advocacy, and international activities. Among other accolades, she's a visiting scholar with RTB, and she's here today to talk about quantum emergence and freedom. Are we bound by the laws of physics? And Dr. Carlson.
All right, thanks for that excellent introduction. Hi, everybody. Hello to the people in the room, and hello to people on Zoom and maybe YouTube later. So the basic framework I want to give you is how to think about the question of the mind and the question of are we free? Do we have actual free will? Can we make decisions? And I'm not a philosopher, as you may know from the credentials that were just stated, but I am a physicist, and so I'm going to tell you the physics that plays into this question, okay? So I just want you to have a good enough background on the physics so you know in these discussions what does the physics say and how far can the physics take you in. So first I want to deal with what makes a physical law fundamental. What makes one physical law more fundamental than another, for example, or why do we call certain ones fundamental and others derived? So this is really the question about how do we go about finding the deepest and truest things about the universe? How do we know what's the deepest and truest? And so for a long time, physicists were working under a reductionist paradigm. And so that's really just a way of thinking about the world, a way of looking at the world. And it's a philosophical take on the world that says the following. It says we're going to learn the deepest and truest things about the universe by finding the smallest bits. And when we find those smallest bits and understand those smallest bits, we will have found the bottom, and that will be the fundamental physics. And so how did we do this? We took materials and smashed them into bits and found atoms, just like the Greek philosophers had predicted, right? And then we took those atoms, and you gave us more money, and we built bigger particle accelerators, and we smashed the atoms to bits and found protons and neutrons and electrons. And then you gave us more money, and we smashed those things to bits. Nobody's found a bit inside of the electron yet, okay? So haven't been able to split that thing yet. But protons and neutrons we can split apart, and it turns out they have quarks inside, all right? And if you give us more money, maybe we'll find things inside of the quarks, but that's going to take a lot of money, okay? So this philosophy of reductionism, that I will find the deepest, truest things about the universe, has given us a lot of mileage in physics, and it's been a reigning paradigm. Now, so this reductionism idea is basically that, whatever it is you're studying, if I go one level lower, I'll find the fundamental bits of the thing you're studying. And then if I go one level lower, I'll find the fundamental bits of that one. So you would say, if you wanted to think about how humans, interact with each other, that's sociology. How one human operates, that's psychology. Physiology, that's based on cell biology and molecular biology. And many body physics is sort of sideways to that. But these are all built out of molecules or atoms. The atoms are made of quarks and leptons. Electrons are a type of lepton. And those we think are made of strings, but we can't really confirm this yet until you give us really big particle accelerators. So that's the reductionist paradigm, and I'm taking a list out of the famous article "More is Different" by Phil Anderson, Nobel Prize winner in my field of condensed matter physics. But then there's this question of, okay, so you do that. Does that necessarily mean that you can build everything back up? If you are a visitor to this universe, I don't know, an alien from another universe, let's say, and we teach you about strings, will you, from how the strings work, will you be able to predict quarks and leptons? And from how those work, will you be able to predict atoms? Would you predict the entire periodic table starting from string theory? from that, would you predict what kinds of molecules we have? Would you predict, higher level things like this cat playing with a butterfly? Would you be able to predict that? And so Phil Anderson's contention is that actually no, this is different. And his point was that more is different. And this is the basic idea that when you get enough constituent particles together, you get new phenomena, and you get fundamentally new physical laws that emerge in the collective behavior that weren't apparent in the constituents. And so, in fact, he argues that you really can't do this. You have to do fundamental science at each new level in order to discover the new emergent laws. So, but this reductionist idea, again, it's given us a lot of mileage. We've gotten a lot of good understanding out of it. So here's the reductionist view, and honestly, it's the reigning view. Okay, so I'm in a tiny slice of physics called condensed matter physics. I'll tell you a little bit about what that is later. But we've moved on from this philosophy. All right, but here's what the reductionist philosophy would give you about the way our physical universe works. So reductionism leads to a very mechanistic and deterministic view of the world. It says the following: look, we're made of atoms, okay? You can go farther down if you want to the quarks and the electrons and the strings, but we're made of some particles, okay? You and me and all the stuff around us, and all these atoms obey laws. They obey physical laws, like, for example, quantum mechanics and electricity and magnetism and gravity, and these are inescapable physical laws. And so the idea is that if we know the positions and the velocities of all of the atoms in the universe, or all the particles in the universe, then we can predict their future because they follow physical laws. So you tell me on this little particle what's the sum total of forces acting on it from all the other particles in the universe, then I know in the next instant which way that particle is going to get pushed, and then I can update everything. So I update my whole calculation. Now, it's a massive calculation. Okay, there's at least 10 to the 80 particles in the universe, which is 1 with 80 zeros after it, which is a lot, you may be aware. So difficult, but in principle, under this paradigm, under this way of viewing the universe, everything is determined. Things just, the physical laws are deterministic. They just lockstep, things go forward. And so everything is determined. And so actually, I love this quote from Susan Blackmore. So she wrote a lovely book called Conversations on Consciousness. She interviewed a lot of people working in the consciousness field, which is a very interdisciplinary, multidisciplinary field. So she interviewed neurosurgeons, biologists, theologians, philosophers, medical doctors, okay, psychologists, everybody who would be working on the ideas of consciousness. And she has this lovely book that just reports on a lot of these interviews with people. But her own preface to the book, she has this lovely thing to tell us. This is her summary. Free will must be an illusion. Wow. Now, kudos to her for being so blunt and to the point about it, okay? But she's working under, she doesn't really explicitly state this, but she's working under the assumption of materialism, that what we are and what we interact with is all physical material stuff, matter and energy, plus the physical laws that control it. And so I totally agree with her that if that's all there is, then yeah, there's no room for freedom, because physical objects follow physical law every single time. That's why we call them laws and not suggestions, right? I mean, can you imagine if like half the electrons in your body sort of decided to go on strike, right? And like tomorrow they're not going to follow the Coulomb law? What's going to happen to your body, You might implode or you might explode. It's not going to be pretty, right? Like either way, we can just agree that that's not something you want. So, she's totally right, though. If everything just lockstep follows these physical laws, that's it. Physical objects follow physical laws every time. That's why we call them laws and not suggestions. So this, we come to this, that, oh my goodness, everything is determined. There's no room for free will, okay? And yet, these guys beg to differ. This is coming across on Zoom in high resolution, but this is ice cream. I like ice cream. Anybody else like ice cream? Okay. So, you walk into an ice cream shop and your reductionist, materialist philosophy about whether or not decisions happen sort of goes out the window, right? Because you have this decision to make, and we all have this impression that we're making decisions. So how do we reconcile this stuff, okay? What's going on? How is it that physical objects follow physical laws every time? There's no wiggle room, and yet when we go to an ice cream shop and we try to choose between triple chocolate chunk brownie and, exhausted parent espresso-based ice cream, we have this impression that we're making a real choice. So here's the questions, right? So the first thing I'll take you through is, can physics come to the rescue? Is there stuff that's actually inherent in physical law that's going to get us out of this? Can we save the materialist, reductionist philosophy and still get free will out of that? Is it possible? So let's go through the two most common things that are cited out of physics to get you out of this. So could quantum help? Okay, was anybody else thinking maybe quantum? But maybe quantum will help you, okay? So quantum indeterminism, all right, can that come to the rescue? Is there stuff in quantum mechanics that leaves us with openness and this gives room for decision-making capacity, right? And so the idea here would be that, okay, as far as we know, individual quantum events are following probabilities, okay? So when an individual quantum event happens, it's like there's a little dice roll that happens, and nobody can predict the outcome. We can predict it at the probabilistic level. So now this makes everybody nervous. When everybody who studies quantum mechanics, whether you're getting deep down into the equations like we do in a physics department or a chemistry department, or whether you're treating it at the philosophical level, nobody likes this, okay? Albert Einstein hated it, in fact, for theological reasons, right? God does not play dice. That was his take. Although I wonder what he would have said about the proverb in the Bible that the lot is cast into the lap and its every decision is from the Lord. So, anyway. Now Richard Feynman had this to say. Okay, so Nobel Prize-winning physicist, and you have to imagine this in his Brooklyn accent because this is actually from a talk. He says, "You don't like it? Go somewhere else, to another universe where the rules are simpler, more philosophically pleasing." Right? He says, "Look, this is just the way it is. This is what we've got." As far as we can tell, it's probabilistic. So here's the question, okay? And this is actually a deep philosophical question about quantum physics and how it operates. When you write down the math for quantum events, we use probabilities and we use statistics, okay? And we make predictions about the likelihood of certain events happening, and then we test that in the lab, and all those likelihood, and if you test it again and again and again and again, you can see that our predictions about the probability are smack on, okay? So they're correct, and they're correct to several places of the decimal. I mean, this is a highly accurate theory. But we don't actually know, and this is something that's not directly taught in a physics class, but the philosophy of science people will tell you about it. We don't know whether that randomness is inherent in the physical system or whether it's a calculational tool, okay? So that is, is the fabric of nature inherently random, or is the fabric of nature inherently deterministic, and we don't know everything about the system, and so the randomness is essentially all in our head. It's just a calculational tool. It would mean that the theory of quantum mechanics is a partial description of nature and not a complete description of nature. This is actually the view that Einstein favored. He felt like it was an incomplete theory of nature. So, and the answer is we don't know. It's just an open question, okay? There's a huge effort right now going on in quantum physics. And in quantum science and engineering in general. You may have heard of the National Quantum Initiative. Has anybody heard about this? The US government and other governments are making massive investments into quantum technologies. And so in the US, this is called the National Quantum Initiative. And so I think we're going to learn stuff. I think we're going to learn things about the foundations of quantum mechanics. So I think maybe, in 10 or 20 years, we might have an answer to this. My personal gut feeling as a physicist who's thought about this very deeply from many angles, I think we're going to find out it's deterministic, but we just don't know. Okay, so it's an open question right now. Now, large objects are still deterministic, even if the fabric of the universe operates on, let's just say that it's the fact that the fabric of nature is inherently random. Even so, large objects are still deterministic, okay? So how do I know that? Well, there's a couple ways. You can think about putting a bowling ball on a slide. Let's just go to the park and we'll put a bowling ball at the top of a slide, okay, where it's clearly going to roll down. And I let that bowling ball go, and it rolls down the slide every single time. No one's ever seen a violation of that. And if someone can turn off the fan, that's great, because you hear this nice buzz in the fan. So it rolls down every single time, even though that bowling ball is comprised of quantum particles. And if the fabric of nature is inherently probabilistic, then each of those little atoms as they move are making little quantum events happen, and those little quantum events are little dice rolls. But yet, large objects are still deterministic. The center of mass of this thing is comprised of something like 10 to the 23 atoms, about an Avogadro's number, actually, several Avogadro's numbers here. So it's a lot of probabilistic events. And in fact, casinos make money off of this, right? So if you do enough probabilistic events, you actually know the general outcome, right? You know, so casinos make money off of probabilistic events. They don't control the dice rolls, right? They're supposed to have fair dice. At least let's assume their dice are fair. Let's assume that their cards are fair and that everything is being dealt out in a fair manner. And yet, because they can make predictions about what happens if thousands of people are playing this game, you know, day after day after day, they know they're going to make money, right? So large scale things that are made up of several distinct probabilistic events are still deterministic. You can still predict things with certainty. And in fact, the larger the object, or the more things that are participating in the process, then the more sure you are that this thing is deterministic, right? And here's the other thing. Let's just say, though, let's say that the random chance is actually inherent to the universe. I'm a skeptic, but let's say it is. Let's say that were the case. Let's say that your impression of free will, your impression of you making a decision about, you know, this ice cream versus the other, deciding between triple chocolate chunk brownie and my favorite Snapple Lantern, which is like, it's a pumpkin flavored ice cream with ginger snap in it. It's really good. Let's say that it's actually just quantum events, little quantum events in my brain that just throw me one way or the other. That's not choice. That's not better, right? It is not an improvement. It's not me choosing. Now it's me being just pushed about by little dice rolls. And I certainly find that not philosophically appealing at all. Okay, so random chance is worse if that were the case. It's not you choosing. It's just you controlled by little quantum events. So then, okay, so quantum didn't help us, right? It might provide some randomness, but it doesn't provide the ability to choose. So then the next physics thing that people think about that might get us around this issue, like, is there room in the physical laws for somehow, you know, some people who, you know, under this assumption would be materialistic objects, just atoms and physical laws? Is there room for us to actually have free will? So Bill Newsom had this to say. Bill's a believer, by the way. He's a professor of neurobiology and the director of the Stanford Neurosciences Institute. And he had this to say. He said, I suspect that answers will ultimately lie in a deeper understanding of emergent phenomena in complex systems. So let's break that down a little bit. So I'll tell you what emergent phenomena is from the perspective of my field of physics. He's in neurobiology, so he's working with very large, high-level objects. I'm in physics. I'm working with very small-level objects, so I'm lower down on the hierarchy. But emergence is a common theme among these. So let me tell you a little bit about emergence. But first, let's consider this famous lady. You guys know who this is, right? Okay. Has anybody been in person to see the Mona Lisa in the Louvre? Okay. So you're getting a better picture of it here anyway, because in the Louvre it's behind a bunch of glass and there's a crowd and you can't see it anyway. So anyway, it's better to just see this picture of it, which of course by now is in public domain. So here's the Mona Lisa. She's famous for many reasons, but one of the reasons is because she's smiling with her eyes. All right, so if you just look at just this part of her, you can still tell that she's smiling, and that's very special. That was considered a new thing. And so now how is it, what is it about this painting that means that she's smiling with her eyes? Now, reductionism is a philosophy that gives you a framework for answering questions, right? So reductionism says, I'm going to find out what's true by breaking things into their smallest bits, right? And we did this with physics and got a lot of mileage out of it, right? We broke the matter into atoms. We broke the atoms into neutrons and protons and electrons. We broke the neutrons and protons into quarks and so forth. So the reductionist would say, I know how to answer this question. I am going to tell you why the Mona Lisa is smiling. Let me at that painting in the Louvre. I'm going to take the cover off, and I'm going to scrape off a little bit of pigment and do a chemical analysis on the pigment, to which all the art lovers, art historians, and art buffs in the room gasped in horror, right? Okay, you don't do that. Anyway, so, all right, but I'll just take it off a tiny bit. You won't even notice, such a tiny amount. So I'll take some of these pigments. I'll do a chemical analysis on the pigments. And by doing that, by breaking it down to its smallest bits, I'm going to tell you why she's smiling. Now, how many people think that's going to work? right? No, not only have we damaged the treasure of the world, but we haven't even answered the question. So basically, reductionism cannot answer every question that is important. And reductionism is it's just a philosophy. It's a philosophical idea about how to go about answering questions. So it can't answer this question for us. It can't tell you everything, and it can't tell you why she's smiling. So here's a different philosophy that comes up in my field of physics, which is emergence. My field of physics is condensed matter physics. I'm sorry, the photo credit's not coming through. Sorry, Uncle David. This is my uncle who took this picture. Photo credit, Uncle David painted. So this is just water. But condensed matter, we mean condensed in the sense of condensation, as in gas condenses to liquid, liquid condenses to solid. So we're about phases of matter and phase transitions. That's what condensed matter physics is about. And basically, if it's an object you can hold in your hand, it's in our domain. Okay? Stars are too big, atoms are too small. I can't hold just one in my hand. But if I can hold a hunk of matter in my hand, then that's condensed matter. That's us. It's stuff you can touch. And so our field has had to move on. We've been forced to move away from the reductionist paradigm because it can't answer the questions we want to answer. So let me give you an example of what that looks like. So this is my cat, Marshmallow, who loved this sink, okay? So why does she have fur? Why does Marshmallow have fur? Is it because A, she's Marshmallow, B, because she's a cat, C, because she's a mammal? Okay, and now we play the Jeopardy music. Do, 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 do. So, what we're looking for, we want to claim, is that the answer that has the broadest explanatory power is going to be the most useful answer. So the most useful answer is this one. It's because she's a mammal and all mammals have fur, right? Some of us have furrier fur than others. But she's got fur because she's a mammal and all mammals have fur. So the answer with the broadest explanatory power is going to be the one we want to go with, right? That's the real reason. The real reason is the broad reason, right? So anybody here like rocks? I have a rock collection. It's really a mineral collection. So it's not just rocks I pick up out of the dirt. It's specific mineral samples and things like that. I saw in the parking lot in here as I was parking, somebody out there is really a fan of flowers. Did you guys see the flower van? You have to see the flower van on the way back. It's got like flowers all over it, little head bobbing flowers on the dashboard and things like that. So that's somebody who's a flower collection. I'm the same enthusiast about minerals, and I have a mineral collection. So we could ask the question, why is this mineral hard? This one is quartz on the left. So, why is it hard? Well, the reductionist would tell you, I'm going to answer your question by breaking it down into its smallest bits. That's the reductionist philosophy. So the reductionist philosophy answers, this quartz crystal is hard because it's made of silicon dioxide. Okay, that's the reductionist answer. I broke it into its smallest bits. That's why it's hard. This is bismuth, another one of my favorites. It's beautiful, isn't it? If you don't have bismuth yet and you have a mineral collection, I encourage you to go get some. It's just beautiful. So this is bismuth. And again, it's hard. And the reductionist answer would be, well, I know how to answer this question. I break it down into its smallest bits. This guy's made of bismuth. Therefore, it's hard because it's made of bismuth. That's the reductionist answer. But that's not a very satisfying answer because they're both hard. There must be some larger level principle, some higher level organizational principle going on, which is what we mean by emergence. There's a new physical law there that comes up in the collective. These are large objects, right? They have at least an Avogadro's number of particles in them. Avogadro's number, you may remember from your chemistry class, is 6.02 times 10 to the 23 constituents. So anything you can hold in your hands has at least that many things in it. So the emergence answer is this. They're both hard because they're both crystalline. What does crystal mean? Crystal means that the constituent atoms or molecules are in some sort of lockstep regular arrangement, like a tiling. So we don't have tile in this floor, but like a tiled floor or a checkerboard or something like that, some sort of lockstep repeating pattern. So a crystal has its atoms in this lockstep repeating pattern in every direction, all the way out to the edge of the crystal. And when that happens, every single time that happens, it's hard. Every crystal you've ever had held in your hand has a hardness to it. This is why rocks are hard. So the larger answer is this. This one has more explanatory power. This is the real reason why they're both hard. So this is the idea that emergence can give us answers to large, when we're talking about objects that are large, emergence is something we should think about. Sometimes this can give us better answers. And so emergence comes up in a lot of different places. It's very prominent in my field. And so another way to think about this is can one person do the wave? So if you've been in a stadium that did the wave, anybody done the wave in a stadium? Okay, so I've done the wave in a baseball stadium, you know. Maybe some people have done the wave like, you know, in a soccer stadium or whatever. I actually tried to do the wave when I was in college. A friend and myself, we went to watch the water polo team at Caltech. Now, Caltech has a great athletics program, but not many students. So we were the only two people in the stands on the Caltech side. We were glad we were there to support the team. And my friend and I said, we're going to do the wave. We're going to really cheer this team on. And we did the wave, and it is exactly as lame as you are picturing in your head. One person cannot do the wave. Two people cannot do the wave. We can just look like fools. But a whole crowd of people can do the wave. All of a sudden, you have enough constituents, and something new can arise, right? One person, not a wave. But a whole collection, a whole crowd, now there's this new thing. And this new thing is a wave. And it turns out that a wave is a wave is a wave. You've seen waves in other contexts. Like, where are some other places you've seen waves? Beach. Ocean, the beach, yeah. Seen waves in other places? The lake, yeah. So lots of water waves. And, you know, how are you hearing my voice right now? Is there a wave associated with that? Yeah, sound waves. So here in the room, you're hearing the sound waves propagate. You know, if you're listening to this online, then, you know, the speaker converted it back into sound, and you're hearing it again through sound. So, but every time a wave comes up, we always use the wave equation, because a wave is a wave is a wave. It doesn't matter what the constituents are. Waves always follow the wave equation. So that's an example of something that's emergent. Waves are waves, okay? And so some of the characteristics of emergent behavior is you need a collective in order to observe it. And yet, it's a fundamental law that came up. You had to do fundamental science at that point to make your organizing idea and then compare it back to data and confirm that your law is correct. All right? And then it has these properties that the wave is somehow now a new thing. So it's a new entity that came up that follows its own new laws. And it's independent of the constituents. It didn't matter who showed up at the stadium that day. Anybody can do the wave. It didn't matter what color their hair was. It didn't matter whether they were in Chicago or whether they were in Rio de Janeiro. Okay? Any crowd can do the wave. So there's some sense in which this emergent phenomena is independent of the constituents. Excuse me. And this happens in lots of different contexts. So I told you about waves and about hardness of minerals, but wetness is another great example. You know, can one molecule be wet? One molecule can be sticky, but not wet. Wetness is a new thing, but liquid water is wet at room temperature. Other emergent phenomena include economies, you know, like if you were an alien and had only met one human being, would you predict the US dollar and the euro and things like that? So economies and currencies are emergent phenomena that collectives emerge out of collectives. Road networks have emergent properties to them. No matter where the road network is, if it's a developed enough area, they'll have hierarchies in their roads, right? They'll have like these main arteries and then less main roads and finally the smallest level roads. Governments are emergent phenomena. You know what kind of government you have, a democracy or a monarchy or whatever. So lots of places that emergent phenomena come up. And so you know, the idea was that, well, maybe this emergent phenomena can give rise to such complexity at the high level, maybe we're going to recover free will out of that. Maybe we can somehow get a you know, like we're complex collective objects, maybe something emerges in us out of those physical laws that leads to free will. So, you know, in the same way then, so we can then ask though, all right, this emergence thing, it's a good idea. It happens in a lot of places. Can it help us answer this question, you know? So reductionism didn't answer the question of why is the Mona Lisa smiling. Is the emergence philosophy going to answer this question for us? And so this is the question of, did this painting just emerge on its own, or is there something else going on? So, you know, again, this gets back to, you know, this quote by Bill Newsom, you know, can emergence rescue us from this issue? Do we get the ability to have free will? Do we get the ability to have consciousness and decision-making power? Specifically, that's what I want to consider, is do we have decision-making power, which includes freedom and agency. And so he said, I suspect that answers will ultimately lie in a deeper understanding of emergent phenomena in complex systems. Maybe it just arises from the collective. Now here's the problem from the physicist's point of view, okay? So from the physicist's point of view, known examples of emergence, the ones we can work out, okay, are all deterministic. So when I mean known, I mean not only do we have the physical laws in mathematics or computer simulations we can write down, but we can do experiments in the lab to test that we're correct. Those places where we have a handle on the whole process, okay, it's deterministic. Every single time, you can't escape this idea that physical objects follow physical laws every single time because they don't have choices. That's why we call them laws and not suggestions. So room temperature water is always wet, right? We have some water bottles up here at the front. Is your water still liquid? Okay, all right, so it's wet, right? Room temperature water is always wet every single time. There's no escaping it. All crystals are always hard every single time. There's no escaping it. You don't get a crystal that flows, right? It does, okay, unless you have a liquid crystal. Okay, it's a different state of matter. It's hard in one direction and flows in the other. Ask me about that later if you like. So determinism is not freedom. It doesn't leave openness, and it certainly doesn't somehow give rise to true agency where you're making decisions. You're still controlled by the physical forces. So emergence doesn't help us. So what I've said is that basically quantum didn't come to the rescue. It's fascinating and has, interesting things in it, and I encourage you to study it, but it's not going to lead to free will, and it's not going to lead to the ability to have agency and make decisions. Or at least to the extent that quantum can provide freedom, it's the kind that's controlled, you're controlled by randomness, okay? And emergence isn't going to save us either, because emergence is ultimately about physical objects following physical laws, and physical objects follow physical laws every single time. They always do the same thing. We're stuck, okay? So is there any way out of this? Now, what I'd like to do, though, is let's look at the take-home messages we can get from emergence. So what are the things that emergence teaches us that might inform this discussion? So emergence teaches us a few things. Lesson number 1, we learn that new entities arise at new levels. In the same way that the stadium doing the wave was a new entity, okay? It's a new property of the system. And also new laws arise at new levels. So the entity would be the wave itself. It's the physical property. The law would be, how does it behave? How fast does it propagate? What shape does it take? That's what the law is going to tell you. So new entities arise at new levels, such as waves. New laws arise at new levels, such as the wave equation. Or in the case of water's wetness, the new entity that arises at the new level is that wetness property. So here's an implication from that, okay? So implication A. This gives us warrant to take high-level observations seriously. High-level observations are meaningful because new information and new objects and new laws are arising at these higher levels. So this gives us warrant to take these high-level observations seriously. So we'll hold that. So what else does emergence teach us? Lesson number 3. Different microscopic situations can lead to the same macroscopic phenomena. In the same way that all crystals are hard independent of what they're made of, there's something new there. A macroscopic, macro meaning large, micro meaning small. So different micro, small level situations can lead to the same macroscopic behavior. That's why we saw that our crystal made of silicon dioxide, the quartz, is hard, and the crystal made of bismuth is also hard, right? So something new arose that was independent of the microscopic. So this is why reductionism can't explain certain high-level behaviors. It just can't. Going deep down gives you the wrong answer, right? It gives you the answer that that crystal's hard because it's made of bismuth, or that crystal's hard because it's made of silicon dioxide, which isn't the right answer. So reductionism can't explain why high-level behavior occurs, and it can give you misleading answers. What else does emergence teach us that bears on this question? So lesson number 4, large-scale phenomena can be independent of the constituents, okay? Lesson number 5, causality can flow top-down in addition to bottom-up. So what does this mean? So often, I mentioned reductionism before, which is going to break things down into their bits. Constructivism would be the reverse, the idea that I could maybe take those bits and construct new things and predict cats just based on the theory of string theory. So causality can flow bottom up. We believe that can happen, but it can also flow top down. So how do we know this, right? All of those experimental results we have, all this scientific knowledge we have about very tiny level things, how do atoms work, how do quarks work, all that stuff, was all set up by people, right? So it was all set up by experimentalists setting up the equipment. And so, of course, causality can flow top down. Of course, causality can flow from the larger part of the system down to the small. That's how we get our experiments done. So it's sort of an implicit assumption that's going on in how we do science. So causality can flow both ways. So now, lesson number 6, all right? Not all large-scale structure is emergent. Some things are in a different category, and I'm going to call those transcendent. So, for example, if you come to my house, okay, or you have someone over to your house, one of the things that a guest might notice first off is the floor plan, how things move, because you have to figure that out in order to get from one spot of the house to the other, right? You have to figure out, well, how is the foyer connected to the living room or the bathroom or the kitchen or wherever you need to go? And so, imagine, you're a guest at my house and you come and you say, oh, look at this lovely floor plan. I like the way that the foyer flows into the living room and flows into the hallway over here. It must be because your house is made out of Indiana limestone and wood, okay, which it is made out of Indiana limestone and wood, but that's not the reason, right? And it's not even an emergent behavior either. It's not as though the builders of my house took that Indiana limestone and wood and threw them up in the air and they self-assembled and boom, out popped my house. And they wish that's how it was done. But they implemented something, right? And in fact, they could have implemented the same floor plan out of any workable house building material, right? They could have built it out of brick. They could have built it out of stone. Would have cost a lot more. But some things are transcendent, so they didn't even arise out of the physical system. They were imposed on the physical system from the outside, like the floor plan of a house. Okay, so let's say, for example, you go and you see a house built by a famous architect. It's like for example, just a few blocks from me, we have a Frank Lloyd I'm going to say it all wrong. Frank Lloyd Wright house, just a few blocks from me, so famous architect. And you walk in there and it's clear that Frank Lloyd Wright had a hand in designing this house. Actually, he designed the whole thing top to bottom, inside out, or he and his team did. And so that's an idea of transcendence. There was something from the outside imposed this structure into the system. And so, for example, when I go into that Frank Lloyd Wright house, I learn a lot about Frank by observing what he did. He's not there, right? He's not there. He's not in the house somehow. His spirit is not living in the house, okay? But I learn about him by studying what he did, and that's another example of transcendence. And this actually gets us back to the Mona Lisa, right? So why is she smiling with her eyes? It's because there's something transcendent that happened, right? Leonardo da Vinci painted her that way. He, from the outside, imposed something on this physical system of the paint and the pigments and how it got put down. And so there's something transcendent behind, So we ask the question, why is she smiling? How is she smiling with her eyes? There's transcendence back there. Somebody put that in. So, is it possible that, in the same way that her eyes are smiling, is it possible that the light in our eyes as human beings, is it possible that the light in your eyes, the light in my eyes, also has a transcendent source, that it's not coming up from the bottom up. It's not coming, the reductionism, isn't giving us the right answer, that it's not even emergent either. Is it possible it's something transcendent and put in there? So I just asked the question, are you really just a bunch of atoms, right? If that's our view of the world, if we view human beings as purely materialistic objects, we're just made of atoms following physical laws, is that a satisfying answer for who human beings are, right? So not only does it not answer our question about freedom, the source of free will, it actually tells you you don't have it. right? It tells you you don't have freedom. If you do have freedom, it's just random chance. And your perception that you're choosing ice creams and you go to an ice cream store is false. It's just an illusion, like Susan Blackmore said. Free will is an illusion. So is that a satisfying answer about who human beings are? And this sort of reductionist view of human beings, not only does it not address things that we think are true about human beings, it also gives us, I think it gives us not a good moral foundation for how we treat each other, right? I mean, I hear this reductionist philosophy echoing around our society, and it doesn't lead you to treat other people well, right? But we're left with this, right? So reductive determinism under the materialist philosophy precludes free will, right? So at least in the sense of agency. So under that view, then, under that worldview, free will does not exist. It just can't. And so what I ask my atheist friends at this point who are working under a materialistic philosophy, are you okay with that? Are you okay with the fact that you think you're making decisions, but you're not? Does that resonate with your actual experience? And of course, the ice cream flavors beg to differ as well, right? When you go into the ice cream shop, we all have this high-level observation that we're choosing between triple chocolate chunk brownie and Snap-a-Lantern, which is a tough decision, but 95% of the time I go for Snap-a-Lantern. So they beg to differ, right? So I would argue that let's take the lesson we got from Emergence. One of the lessons we got from Emergence was that high-level observations are meaningful. So I would say our high-level observations that we really do make decisions are meaningful. We should not throw out data like that just because we don't understand how to connect it to the reductionist idea, just because we don't understand how to make all that go together. We should not throw out billions of people's high-level observation that we all make true decisions with true freedom and with true choice. That's throwing data out, right? So I'd argue these high-level observations are meaningful. So again, going beyond emergence though, right? Going beyond reductionism, beyond even emergence, implication C to all this discussion would be that there must be something more. There must be something more than physics and chemistry. There must be something more than the material world. If our high-level observation that we all make decisions is correct, then there must be something more. And I would argue that, by golly, if your brain is lying to you about something so fundamental, why should you trust it about all the other stuff it tells you? Okay? So take this high-level observation meaningful. There must be something more than the physical world, which I would argue leads us to the spiritual world. Okay? And that's as far as I as a physicist should go. If you want a deeper discussion, you've got to get a philosopher in here or a theologian. But that's what I wanted to leave you with, is this idea that there must be something more than the physical world. Do people have any questions about that? I'm happy to take questions.